Your kid just built their 20th Scratch project, dragging and dropping blocks like a pro, but now they're asking how real programmers do it, and you realize the cozy world of visual coding just hit a wall. That jump from blocks to actual typed code, the kind engineers use to build Mars rovers and warehouse robots, is where most young learners either break through or burn out. I'm Lakshmi Venkataraman, and I've spent years guiding students through exactly this transition in my work with STEM education. You're listening to the STEM Lab podcast. Quick note up front. Everything you're about to hear, the research, the advice, the structure, comes from real educators and has been fully reviewed and written by humans. The voice you're hearing, though, that's AI generated, which lets us get episodes to you faster without compromising on accuracy. If you've been listening for a while, thank you. Seriously, it's great having you here week after week. And if this is your first time tuning in, welcome. We release new episodes every Monday, Wednesday, and Friday, covering everything from robotics kits to teaching strategies to toy reviews. Let's get into today's topic. You've watched your learner master visual programming, dragging blocks, sequencing commands, debugging with colorful feedback. Now they're ready for the next milestone, writing actual code that professional engineers use. This guide walks you through the transition from block to text robot coding, a pivotal moment in any STEM learning path that bridges playful exploration with industry standard skills. You'll learn how to scaffold this shift strategically, which platforms ease the jump, what cognitive leaps to expect, and how to prevent the frustration that derails so many young programmers at this stage. This process typically takes 8 to 12 weeks with consistent practice, 2 to 3 sessions weekly. It targets learners ages 10 to 14 who've completed at least 20 to 30 hours of block-based programming. By the end, your student will write functions, debug syntax errors, and control real hardware using Python or Arduino C++, the same languages used in robotics labs worldwide. Now, let's talk about what you'll actually need to get started. On the technical side, your learner should have at least 20 to 30 hours under their belt with Scratch, Blockly, or something similar. They need to be comfortable reading at around 4th grade level or above because coding means decoding error messages and documentation. Basic algebra understanding helps, variables, expressions, simple equations, and they should be able to type at least 15 words per minute with basic punctuation accuracy. For hardware and software, you'll want a programmable robot platform that supports both block and text modes. Check the link below to see current pricing on options like Lego Mindstorm's Robot Inventor, Vex IQ Robotics Kit, or Arduino Robot Car Kit. Your computer needs to run Windows 10 or 11, Mac OS 10.15 or newer, or Ubuntu 20.04 or later. 4 gigs of RAM minimum, 8 recommended. You'll need a development environment. Python 3.9 or newer with IDLE or Thonny IDE works great, or Arduino IDE version 2 and up. Don't forget the USB cable to connect robot to computer. Check whether yours uses USB-C, micro USB, or USB-A. And you'll want reliable internet for initial downloads and documentation access, though many IDEs work offline after setup. Keep a notebook or digital document handy for code snippets and debugging notes. You might want to look at the robotics kit compatibility checklist to verify your platform supports text-based languages, and grab the reference guide for your chosen robot's API or library documentation. Moving on to step 1, choosing the right platform. Your first strategic decision determines everything that follows. Select a robot platform that offers both block-based and text-based programming for the same hardware. This continuity is crucial. When students see identical robot behaviors produced by blocks one day and text the next, they build schema around the idea that code is simply another way to express the same logic, not a completely foreign skill. Lego Mindstorm's Robot Inventor excels here. Check the link below for current pricing. Its Scratch-based environment lets students export block programs as Python code, providing a direct comparison. Similarly, platforms like Vex IQ bridge Blockly to C++, and many Arduino-compatible robots offer Blockly wrappers that generate visible C++ code below each block workspace. Here's what to verify. Does the platform support live code switching, toggling between block and text views of the same program? This feature reduces cognitive load dramatically. Check software compatibility. Some platforms require specific OS versions or cloud accounts. For example, Lego Mindstorm's Python environment requires Bluetooth connectivity and works best on Windows or Mac OS rather than Chromebooks. Vex's text-based Vex code compiles locally but requires admin privileges to install drivers. I've watched hundreds of sixth graders struggle when they jump to text-based coding using entirely new hardware. The double novelty, new syntax, and unfamiliar motors and sensors overwhelms working memory. A hybrid platform lets them focus on language syntax while working with motors, sensors, and chassis they already understand intuitively. Look for robots with extensive documentation in both formats, active user forums, and clear API references. Poor documentation is the silent killer of text-based transitions. Think about durability, too. Will this platform grow with your learner? The best transition robots support expandability, additional sensors, third-party libraries, integration with professional tools. A robot that caps out at introductory text-based code becomes a stepping stone you'll replace within a year. Prioritize platforms with paths toward advanced concepts like object-oriented programming, sensor fusion, or ROS integration if your learner shows serious interest. Step 2 is all about dual-view programming to build conceptual bridges. Don't delete the block interface yet. Your most powerful teaching tool during this transition is simultaneous comparison. Start every new concept by building it in blocks, then immediately view or write the equivalent text code. This parallel exposure builds what cognitive scientists call representational fluency, the ability to recognize the same idea expressed in different symbolic systems. Begin with the simplest possible program. Make the robot move forward for 2 seconds. In Scratch or Blockly, this might be 2 blocks. Show your learner the text equivalent, something like robot.move_forward open parentheses 2 close parentheses in Python, or motor.spin open parentheses forward, 2, seconds close parentheses semicolon in C++. Point out the structural parallels, the action verb, the parameters, the syntax markers like parentheses and semicolons. Layer complexity gradually. Next session, add a turn, then a loop that repeats the forward turn sequence. Each time, construct the block version first, discuss what it does, predict what the text version will look like, then reveal the actual code. This prediction step is critical. It activates prior knowledge and makes the text code feel like a puzzle to solve, rather than arbitrary symbols to memorize. Many modern platforms offer code preview features where the text updates live as you manipulate blocks. Lego Mindstorms and Vex both implement this beautifully. Use it liberally for the first 4 to 6 sessions. Students should spend roughly 60% of their time in block view, 40% reading the generated text, asking questions like, why does this line have a semicolon but that one doesn't? Or, what happens if I change this number in the text? Will the block update? Here's where I see parents rush. They assume once a child gets it after 2 or 3 examples, they're ready to write from scratch. Not yet. You're building neurological pathways, not just transferring information. Research on cognitive load theory suggests we need 10 to 15 repetitions of a concept in varied contexts before learners can apply it independently. Create those repetitions by building 8 to 10 different programs in dual view mode before attempting pure text-based coding. Let's talk about step 3, introducing text-first challenges with extensive scaffolding. After your learner has decoded 8 to 10 dual-view programs and can accurately predict text syntax from block patterns, it's time to flip the script. Text-first challenges. But don't just hand them a blank IDE and say, make the robot dance. That's pedagogical malpractice. Instead, provide heavily scaffolded exercises. Start with fill-in-the-blank programs where 80% of the code is written and they complete specific lines. For example, you might write a comment that says, make the robot drive in a square, then set up a for loop with function calls where they just need to fill in the distance and degree parameters. This structure lets them focus on parameter values and logic flow without wrestling with syntax they haven't internalized yet. Gradually reduce the scaffolding. Next exercise, provide function names but no parameters. Then provide only comments describing what each line should do. Finally, give them a behavior goal with no code template. Debugging becomes your primary teaching tool here. Introduce deliberate errors in your scaffolded code, a missing parentheses, a misspelled function name, an incorrect indentation. In my classroom, I call these bug hunts, and they're more valuable than writing perfect code. When students fix these errors, they're learning to read compiler and interpreter messages, a skill that separates frustrated quitters from resilient programmers. Python's error messages are generally more readable for beginners. You'll see things like syntax error, invalid syntax with a line number. Arduino C++ errors can be cryptic, like expected semicolon before robot. Choose your first text language accordingly. Here's a reality check on timing. Most learners need 3 to 4 weeks of scaffolded text exercises before they can write a novel 15 to 20-line program independently. That's 6 to 8 sessions if you're meeting twice weekly. Rushing this phase creates brittle knowledge. Students memorize specific examples, but can't transfer the patterns to new problems. Step 4 is where things get cognitively demanding, teaching syntax rules explicitly through error pattern recognition. Block-based programming protects students from syntax errors. You can't drag blocks into invalid configurations. Text-based programming is unforgiving. A missing semicolon, a lowercase letter where uppercase is required, or incorrect indentation halts the entire program. Don't leave syntax learning implicit. Create a reference sheet that explicitly teaches your chosen language's rules. For Python, that means indentation matters. 4 spaces after colons in loops, conditionals, and functions. No semicolons needed. Function calls require parentheses even with no parameters. String text needs quotes. Variables are case sensitive, so capital S speed and lowercase speed are different. For Arduino C++, every statement ends with a semicolon. Indentation is stylistic, but good practice. Curly braces group code blocks. Function calls need parentheses and parameters. Case sensitive throughout, and you must declare variable types like int speed equals 50 semicolon. Build these rules through error pattern recognition exercises. Show students 5 broken code snippets and ask them to identify the error category, missing semicolon, wrong indentation, misspelled function, before fixing them. This metacognitive step, naming the error type, helps students develop internal debugging checkers. When they write their own code later, they'll instinctively pause and ask themselves, did I close that parentheses? Is my indentation consistent? The vocabulary matters. Students often say, it's broken or it doesn't work. Train them to use precise language. I'm getting a syntax error on line 7, or the compiler says there's an unexpected indent. This precision shifts their mindset from coding is mysterious and unpredictable to coding follows rules I can learn and apply systematically. Now we're on to step 5.
Practice code translation exercises in both directions. Fluency requires bidirectional translation. Students should be able to convert block programs to text and visualize what text code would look like as blocks. This back and forth solidifies conceptual understanding in ways that unidirectional work never achieves. Try block-to-text translation first. Provide a 10 to 15 block program that makes the robot navigate a simple obstacle course. Ask your learner to write the equivalent text code without using the auto-generate feature. They should refer to their syntax reference sheet and previously written programs. When they finish, run both versions and verify identical behavior. Then try text-to-block reverse engineering. Give them a text program you've written or found in documentation examples and ask them to sketch what it would look like as blocks on paper. This mental visualization exercise strengthens their ability to read code, to see loops, conditionals, and sequences as structural units rather than character-by-character text. For mixed translation debugging, present a block program and its supposed equivalent text code, but introduce subtle differences. Maybe the block program turns 90 degrees, but the text code turns 85 degrees. Students identify the discrepancies and decide which version is correct based on the stated goal. These exercises take 20 to 30 minutes each and should be distributed across 4 to 6 sessions. They feel tedious to some learners, especially those who just want to build cool robots, but this is where you leverage your authority as the educator to insist on foundational skill building. In my experience, students who skip translation practice hit a wall around conditionals and nested loops. They can copy examples, but can't adapt them to new situations. Why this works neurologically? Translation activates different cognitive pathways than single-direction programming. When students convert blocks to text, they're retrieving syntax rules from memory. When they visualize text as blocks, they're applying abstract comprehension to spatial representation. This dual encoding makes the knowledge more durable and transferable to novel problems, precisely the outcome you need before advancing to complex projects. Moving on to step 6, introducing variables and functions using robot-specific examples. Once students can write basic sequential programs, move, turn, wait commands, the next conceptual leap is variables and functions, the building blocks of modular, reusable code. This is where text-based programming diverges dramatically from block-based work. While blocks often abstract variable management, text code forces explicit declaration, type specification in C++, and scope understanding. Start with variables tied to physical robot behaviors. Instead of hard-coding robot.move_forward 50 everywhere, introduce a variable called distance that equals 50. Then call robot.move_forward with distance as the parameter. Then modify distance in one place and watch all movement commands update. This demonstrates variables' power. They let you adjust behaviors globally without hunting through code. Make it tangible. You're building a maze-solving robot. The maze dimensions change weekly. Would you rather change 15 lines of code or just change one variable at the top? Functions come next. After writing the same turn 90 degrees and move forward 30 centimeters sequence 5 times, students feel the pain of repetition. Introduce functions as labor-saving tools. Define a function called square turn that does the turn and move, then just call that function 4 times. The transition accelerates here because text-based functions are far more flexible than block-based custom blocks. Students can add parameters, return values, and create libraries of reusable behaviors, skills directly transferable to professional software engineering. Some robot platforms, especially Arduino-based kits, require you to define functions before setup or loop, while Python is more forgiving about function placement.
Teach the conventions of your chosen platform explicitly. Arduino's requirement that functions appear above their first call or be declared with forward declarations confuses many beginners who come from Python's more relaxed structure. I've seen students grasp variables quickly, but struggle with function scope, why a variable defined inside a function isn't accessible outside it. Use robot examples. This variable is like the robot's memory while it's executing this specific task. Once the task ends, that memory clears. If you need to remember something longer, define the variable outside the function. Physical metaphors stick better than abstract explanations about stack frames and namespaces. Step 7 brings us to conditionals and loops with sensor-driven logic. The final piece of foundational text-based robot programming is conditionals, if-else statements, and loops, the control structures that make robots respond dynamically to their environment. This is where your learner transitions from choreographing predetermined movements to writing robots that make decisions. Start with sensor-driven conditionals. If your robot has an ultrasonic distance sensor, you might write, if robot.distance is less than 20, robot.turn_right 90, else robot.move_forward 10. This simple structure, if there's an obstacle within 20 centimeters, turn, otherwise keep moving, mirrors real autonomous vehicle logic. It's not a toy example. It's the foundation of collision avoidance systems in warehouse robots and self-driving cars. Frame it that way to maintain engagement.
Loop syntax varies significantly between languages, and this is where students who mastered loops in blocks sometimes stumble. A scratch repeat 10 block becomes for I in range 10 : in Python, or for open parentheses int I equals 0 semicolon I less than 10 semicolon I plus plus close parentheses in C++. The Arduino C++ version, with its three-part structure, confuses many learners initially. Break it down explicitly using the robot's behavior. Initialization, int I equals 0, means start counting at 0. Condition, I less than 10, means keep looping while the count is less than 10. Increment, I++, means add 1 to the count after each loop. Then show how all three pieces work together to repeat the motor command exactly 10 times. Run the program with a serial monitor or console output that prints I each iteration so students see the count incrementing. While loops introduce a new complexity, loops that continue until a condition changes, not for a predetermined count. A classic robot example, while robot.distance is greater than 20, robot.move_forward 5, then robot.stop. This loop runs indefinitely until an obstacle appears within 20 centimeters. It's perfect for teaching the difference between counted iteration with for loops and condition-based iteration with while loops. But it's also where students write their first infinite loops accidentally. When the robot never stops moving because the condition never becomes false, they learn the critical importance of loop exit conditions. Use these mistakes as teaching moments. Don't rescue them immediately. Let them watch the robot crash into a wall safely with low motor speeds while their while loop runs forever because they forgot to update the conditional variable. Then debug together. What would need to change for this loop to stop? How do we make sure that thing actually changes? These control structures position your learner as the bridge between beginner and intermediate programming. Once students master sensor-driven conditionals and loops, they're ready for multi-sensor fusion, state machines, and eventually ROS-based programming used in research labs and industry. Step 8 is where everything comes together, graduating to independent projects with incremental complexity. Your learner has now completed 8 to 12 weeks of structured transition work. They can write basic Python or Arduino C++ programs that control motors, read sensors, use variables and functions, and implement conditionals and loops. The final step is independent project work, not following tutorials, but designing and implementing their own robot behaviors from scratch.
Start with constrained creativity. Design a robot that navigates a 3-foot square course and returns to its starting position. You must use at least one loop, one function, and one conditional. These parameters provide enough structure to prevent choice paralysis while requiring students to synthesize all the skills they've developed. Many families stop too soon when students can kind of write code with heavy reference to examples, but true skill transfer, the ability to apply programming knowledge to genuinely novel problems, requires 3 to 5 independent projects of increasing complexity. Structure a progression. Week 9 to 10, a line following robot using a single light sensor, 30 to 40 lines of code. Week 11 to 12, an obstacle-avoiding robot with distance sensor and turn decision logic, 50 to 60 lines. Week 13 to 14, a maze-solving robot combining multiple sensors, functions for different behaviors, 80 to 100 lines. Week 15 to 16, student's choice. Design and implement a behavior, minimum 100 lines with modular function structure. Debugging becomes the primary learning activity during independent projects. Students will write code that doesn't work on the first attempt. That's normal and healthy. Your role shifts from instructor to consultant. Ask guiding questions rather than providing solutions. What does that error message tell you? What line is it happening on? What's the value of that variable when the error occurs? How could you check? This is also when expandability and durability specs matter intensely. Can your robot platform accommodate additional sensors for Project 3? Will it physically withstand the repeated testing and crashes inevitable during maze-solving work? Check the link below for the VEX IQ Robotics Kit, which handles this progression well. It's modular, supports both Python and C++, connects to dozens of sensor types, and its metal construction survives thousands of test runs. Budget platforms with limited expandability become frustrating constraints at this stage. Documentation skills emerge here too. As projects grow beyond 50 lines, students need to comment their code, organize functions logically, and potentially collaborate with others. Introduce professional practices. Before you write any code, write comments describing what each section will do. Then fill in the actual commands. This top-down approach, common in software engineering, prevents the spaghetti code that results from diving straight into writing without structure. If your learner succeeds at all 4 independent projects, writing functional, sensor-responsive robot code largely without reference examples or heavy guidance, they've completed the transition from block to text robot coding. They're now positioned to explore advanced topics: object-oriented programming, library integration, integration with platforms like Raspberry Pi for computer vision tasks, or even ROS for multi-robot systems. Let's talk pro tips and common mistakes.
First tip, use serial or console output liberally. The biggest difference between block-based and text-based debugging is visibility. Blocks often show real-time feedback on screen. Text code runs invisibly unless you add print statements in Python or serial.println in Arduino C++. Teach students to output variable values, sensor readings, and checkpoint reached messages throughout their code. This practice mirrors professional debugging with logging tools. Second tip, build a snippet library. Create a shared document where students save every working code snippet, motor controls, sensor readings, loops, functions. When they start new projects, they copy, paste, and adapt rather than writing from scratch every time. This is exactly how professional programmers work. No one memorizes every syntax detail. Common mistake number 1, attempting object-oriented programming too early. Classes, objects, inheritance, these concepts are powerful but premature during initial text-based transition. Students need 6+ months of procedural programming, functions, variables, basic data structures, before OOP makes sense. Introducing it earlier creates confusion that undermines confidence. Common mistake number 2, inconsistent practice cadence. Programming skills atrophy faster than you'd expect. 3 sessions per week for 4 weeks builds more durable knowledge than once weekly sessions for 12 weeks, even though total hours are similar. The brain needs frequent reinforcement while forming new neural pathways. If your schedule only allows once weekly sessions, assign short 15 to 20-minute practice exercises between meetings. Common mistake number 3, comparing your learner's pace to online examples. You'll encounter claims of 10-year-old codes Python robotics in 2 weeks. Ignore them. Those stories omit crucial context, prior experience, adult assistance, existing math and logic skills. Your learner's trajectory is individual. The goal isn't speed, it's building genuine understanding that transfers to novel problems. Another tip, celebrate compilation success before execution success. When a student's code compiles or runs without syntax errors, even if it makes the robot do something wrong, acknowledge that milestone. Your code is grammatically correct. Now let's fix the logic to make it do what you intended. This separates syntax mastery from algorithmic thinking, making debugging less overwhelming.
Now let's address some frequently asked questions. How long does the transition typically take? The transition from block to text robot coding typically requires 8 to 12 weeks with consistent practice, 2 to 3 sessions of 45 to 60 minutes per week. Individual timelines vary based on prior experience, age, and typing proficiency. Students who've completed 30+ hours of block-based programming and have basic algebra understanding usually progress faster than those with minimal preparation. You'll know the transition is complete when your learner can independently write a 100+ line program that uses variables, functions, conditionals, and loops to solve a novel problem with minimal reference to examples, which usually occurs around week 12 to 16 of structured practice. Should we transition to Python or Arduino C++ first? Choose Python if your learner is 10 to 12 years old, prefers readable syntax, and wants to eventually explore AI, machine learning, or data science applications. Python's versatility makes it an excellent first text language that transfers to countless domains beyond robotics. Choose Arduino C++ if your learner is 13+ years old, specifically interested in electronics and embedded systems, and plans to work with industry-standard microcontrollers. Arduino C++ teaches low-level hardware control and memory management concepts essential for engineering careers, though its syntax is less forgiving for beginners. Many families successfully start with Python for 6 to 8 months, then introduce Arduino C++ as a second language once text-based programming fundamentals are solid. Can my child transition directly from block-based to text without a hybrid platform? Transitioning directly from block to text robot coding without a hybrid platform is possible, but significantly harder. Students must simultaneously learn new syntax rules and new hardware behavior, which overloads working memory and increases frustration. If you don't have access to a hybrid platform, mitigate the difficulty by using the same robot hardware throughout the transition, keeping motors, sensors, and chassis familiar while introducing text-based programming through detailed translation guides that show block-to-text equivalents for every command your learner already knows. This approach requires you to create those translation documents manually, which is time-intensive but pedagogically sound if hybrid platforms aren't available. What signs indicate my learner is ready to transition from blocks to text? Your learner is ready when they can independently build block-based programs with 30-plus blocks that include loops, conditionals, and variables. They should be able to explain what their program does line by line without running it, debug logical errors by predicting outcomes and testing systematically, and demonstrate comfort with sequential thinking and basic algebra concepts like variables and expressions. Additionally, they should type at least 15 words per minute with basic punctuation accuracy and show intrinsic motivation to understand how the code really works rather than just making the robot move. Curiosity about the underlying mechanics is the strongest predictor of transition success in my classroom experience with hundreds of middle schoolers. Here's the summary. The transition from block to text robot coding represents one of the most significant milestones in a young programmer's development. It's the bridge from visual exploration to industry-standard skills. By choosing hybrid platforms, starting with dual-view programming, scaffolding text-first challenges carefully, teaching syntax explicitly, practicing bidirectional translation, mastering variables and functions, implementing sensor-driven logic, and graduating to independent projects, you'll guide your learner through this cognitive leap systematically. This 12 to 16-week journey demands patience, consistent practice, and strategic scaffolding, but it positions students to write real code used in professional robotics labs, autonomous vehicles, and manufacturing systems. Your role isn't to accelerate the timeline, it's to build durable understanding that transfers across programming languages, platforms, and problem domains for years to come. That wraps up this episode of the STEM Lab podcast. Thanks for spending this time with me. We'll be back with a new episode every Monday, Wednesday, and Friday. If this one was helpful, I'd genuinely appreciate it if you could leave a 5-star rating and write a quick review. It's one of the biggest ways other parents and educators discover the show, and it helps us reach people who are looking for exactly this kind of breakdown. And go ahead and hit subscribe or follow so you get notified the second a new episode drops. Talk soon.